Today, we're going to be talking about the normal distribution. So, what's the normal distribution useful for, first of all? Why is it helpful? Well, here's the situation, right? I have, let's say, 500 people. In New York City, they're considering banning cigarettes in public parks. Now, it says in the general election or a general survey from the New York Times that 65% of New Yorkers support banning cigarettes in public parks, which is good. I don't want people smoking in public parks either. So then you pick 100 random New Yorkers from a sample. What is the chance that at least 65 of them say no to cigarettes in public parks? That's the question that the normal distribution was made to answer. But first of all, why the normal distribution? Well, there's one very simple reason. Is there a calculator here? Here it is. Okay. So, let's try to do that cigarettes problem. Is it frozen? The heck? Alright, stop graphing. I think you're, that's bad. Okay, so I'll continue while you look for it. So, here's the question, right? I have a survey from the New York Times. I have a survey from the New York Times. I don't actually remember how the New York Times logo looks, but I hope that this is a good representation. The New York Times is telling me 65% of people in New York City do not want to allow cigarettes in public parks. So now, here's the question. I am going to go to Times Square and ignoring the bias of walking into Times Square, since of course, basically you're only surveying Manhattaners, and they're in a much denser part of the city, and a lot of people who are concerned about public parks. If we ignore all that bias and say that I just grabbed 10 random people off the street of Times Square, what's the chance that more than 6.5 of them, 65%, are going to say that they don't want cigarettes in public parks? Okay, well, let's see. There are 10 people that we're going to interview in Times Square. For each one of them, ignoring statistical bias, there's a 65% chance they're going to say no to cigarettes, and a 35% chance they're going to say cigarettes should be allowed. So then, what's the probability that I get more than 65% of them, which is more than 6.5, but of course you can't have 6.5 people saying yes, so it's going to be greater than or equal to 7. What's the chance that greater than or equal to 7 of them say that they don't want cigarettes? Well, now all you have to do is take 0.65, raise it to the 7, multiply it by 0.35, and raise it to the third. And that's it, right? Oh, no, wait a second. There were so many different ways that 3 of our 10 people could answer no. In fact, 10 choose 3 ways, also known as 10 factorial over 3 factorial times 7 factorial ways. Oh, wait a second. That's not even right, because you also have to add on the chance of 8 people saying no to cigarettes. Oh, and you have to add on the chance of 9 people saying no to cigarettes. Oh, and you have to add on the chance that all 10 of the people you surveyed turn out to be anti-cigarette. So, I mean, how long will this take to sum up? Now you have to calculate. Well, this is going to be 10 factorial. Where's the factorial button? Is there even one here? That is not good. 8 times 7 times 6 times 5 times 4 times 3 times 2. So, just noting down some values here so I can calculate this a little bit more efficiently. 10 factorial is 362,8800. So what is this going to give you? Well, you get 362,8800 divided by 3 factorial, which is 6, and 7 factorial, which is, man, this calculator sucks. 42 times 5 is 210. 4 is 840. 3 is 2520. 2 is 5040. Okay. Where's the syntax? Okay. So 10 choose 3 is 120 times 0.65 to the 7 times 0.35 to the 3. 10 choose 2, 362,8800 divided by 2 factorial times 5040 times 8 is 45. This is going to be 9. And that's just 0.65 to the 10. So, I mean, what happens when you add up all of these? 120 times 0.65 to the 7 times 0.35 to the 3. Where is the syntax error, old man? So this is about 0.252. This oh wait a second. Oh wait, I accidentally added instead of multiplying. I think I might be a little bit dumb. 8 times 0.35 to 2. 0.1757. 9 times 0.65 to the 9 times 0.35, about 0.065, and 0.65 to the 10 is about 0.013. And so, summing all of those together, you get 1757.065.013. Around 0.5059. A 50%, or maybe 51% if you liked rounding up, chance that 7 people will say no. See how comically long it took just to calculate that number? But look, we have a solution for you. Well, actually, Demoivre. Or if you want to credit Gauss instead, Gauss has a solution for you. Whenever the standard variance of the binomial distribution, which is what we just calculated, is around the middle, the binomial distribution starts taking on a nice bell shape. And you know what approximates this bell shape really, really, really well? This function. And what's the benefit of this function? Well, for one, its integral is 1, so it counts over the entire real line. But for second, it's pretty generalizable, unlike the binomial distribution, which only works for integers. This bell curve can take in any real value of x. But third, and most importantly, the binomial distribution was so hellish to calculate. Now let me ask you a question from like a real survey. A real survey doesn't just survey 10 people. It might survey 1,500, maybe even 2,000. Let's see what happens if I ask this calculator to calculate 2,000 factorial. 2,000 times 1999 times 1998 times 1997, 1996, 1995, 1994, 1993. Hell, let's just go 1990 squared times 1980 to the 10. Okay, it's still surviving. 1970 to the 10 times 1960 to the 10 times 1950 to the 10 times 1940 to the 10. Oh, and it topped out. Error overflow. So, as you can see, calculating choose functions for even these low values is extremely taxing on this little calculator. And now imagine what an even bigger survey could do. Could break even the most advanced calculators. Not to mention that you don't just have to calculate 10,000 factorial once, you have to calculate it so many times over and over because you have to add all of these probabilities up. But the normal distribution throws all of that out the window. Because now you can just ask the binomial distribution, hey, if I said x is greater than a certain number, what is the value of the integral from here to infinity? And the normal distribution answers for specific cases with an almost perfect approximation. This doesn't always work, however, because sometimes for especially low sampling values or especially high ones, the binomial distribution is going to have a skew. But here's the thing about the normal distribution. It never skews. Its third moment is always 0. And so is its fifth moment, seventh moment, seventh moment, ninth moment, and so on and so forth. Only its even moments are non-zero. And, of course, its even moments are always non-zero. If all of its moments were 0, it would just be the zero distribution. So that's all about the normal distribution and why it's hailed as one of the greatest inventions in mathematics.